The next thing I want to talk about are inverse functions. Let's let f be a one-to-one function. Then g is the inverse of a function f if I take f composed with g and it equals x, and if I take g composed with x, it equals x. In that case, we could write g as f inverse of x. So friendly reminder, section 1.1 function composition, it's not multiplication. What I'm doing is I'm substituting g of x in for x in f. And if I took g composed with f, I'm substituting f of x into x for g. Right? So these would be two inverse equations. When something's an inverse, it undoes the other. So for example, if I have the point when x is 1, y is 3 on my graph, the inverse function is going to have when x is 3, y is 1. My x's go to my y's and my y goes to my x's. So for a one-to-one function containing the point AB, the inverse of f will contain the point BA. So here we have two functions that are relations, right? A set of ordered pairs is a relation, but they could also be a function, which these are. And they're one-to-one too. So if I have f and g and their inverses, for every x value, it's going to go to y, and every y value is going to go to x. And those ordered pairs stay. They're just flipped. So here I have -1 goes to -1, y goes to -1. 0 goes to 0, 0 goes to 0, my x goes to y, and my y goes to x. So these two functions are inverses. So how do I tell if two functions are inverses? Well, I can tell if the two functions are inverses by taking function composition both ways and seeing if it equals x. Note, if I compose f and g and I get x, I have to compose g and f. But if I compose f and g and I don't get x, I can stop because I know they aren't functions. So let's go ahead and take f composed with g of x. I feel like this green is hard to see. Maybe that's just me. So I'm going to have f of g of x. So I'm substituting g of x in for x. So that's going to give me the cube root of x plus 1 cubed minus 1. Well, cubes undo cube roots. So I have x plus 1 minus 1, which equals x. Awesome. So I've done function composition one way. Now I have to do it the other way. So I'm going to take g and substitute f of x into it. So now I have the cube root of, instead of x, I have x cubed minus 1 plus 1. This is going to simplify to the cube root of x cubed, which is x. So these two functions are inverses. Woohoo! Another thing to check, and I didn't start out with this, so first thing to see if functions are inverses, we need to visualize them and do the vertical line test. So for example, this is a cubic, right? It's going to look something like this if I was to visualize it. So it does pass the vertical line test and the horizontal line test. I just didn't draw it very well. So it's definitely a function. Here I have my cube root. That looks something like this. So it does pass the vertical and horizontal line test. So make sure they're functions that are one-to-one before you even try and see if they're inverses, right? That's going to save you a lot of work, and I wish I'd thought to do that when I was in college. So what you want to be aware of are parabolas, right? These are functions, but they're not one-to-one. So no degree 2 equations. That also goes for degree 4, right? No really even degree equations. So let's take a look at problem 2. So f of x is a linear equation. It's a degree 1 equation. G of x is a linear equation. It's a degree 1 equation. So both of these would pass the horizontal and the vertical line test. But you always want a vertical line test first. So let's go ahead and compose the two. If I have f composed with g of x, that's going to be f of g of x. So I'm plugging g of x in for x. So I have -3 times g of x, which is -1/3 x minus 12 plus 12. Okay, this looks promising. That means I have negative 3 times negative 1/3 x. That just leaves me with x. Negative 3 times negative 12 is a positive 36 plus 12. So I get this is equal to x plus 48. Do I need to go ahead and solve the other direction? No, these are not inverses because it both have to equal x. Let's take a look at example 3. Let's change colors back to green. Maybe I'll regret it. If I have f of x equals 2x plus 4, that's a linear equation, so it is a function and it is 1 to 1. If I have g of x equals positive 1/2 x minus 2, that is a linear equation and it is 1 to 1. So I'm going to want to take my function composition. So I'm going to plug g of x in for x and f. And remember, we did all this function composition. If you have questions on it, go back and look at the section 6.1 videos. So I have 2 times 1/2 x minus 2 plus 4. That gives me x minus 4 plus 4, which is x. Woohoo! Now I need to check the other direction. So I'm going to take g of f of x. So I'm going to plug f of x in for x and g. So I have 1/2 times 2x plus 4 minus 2. That gives me x plus 2 minus 2, which is x. So these functions are inverses. Woot woot. Now, what if I want to find the inverse of a function? So if I'm given a 1-to-1 function defined by y equals f of x, I can find the equation first by interchanging x and y, solving for y, and then rewriting y as f inverse of x. So this makes sense, right? As inverse functions change your x and y, that's what we're doing. And then if I solve for y, that gives me the equation for my new function. So let's work through a couple examples of these. Always remember to check and make sure your function is 1 to 1 before you go through this process. So I have f of x equals 2x plus 5. That's a linear equation. It's 1 to 1. It's a function, so we're good to go. I'm going to, instead of having y equals, here's number 1, y equals 2x plus 5, I need to switch them. So I'm going to have x equals 2y plus 5. Now I have to solve for y. I'm going to subtract 5 from both sides. I get x minus 5 equals 2y. I divide both sides by 2. I get 1/2 x minus 5/2 equals y. So f inverse of x equals 1/2 x minus 5/2. And friendly reminder that if you want to check your answer, you can just go back and use the function composition both ways to make sure you got your answer correctly. Composition. All right, let's take a look at problem 2. That's a degree 2 equation. That's a parabola. It's a function, but it's not 1 to 1. So that means the inverse does not exist. D and E does not exist. My last example, f of x equals x minus 2 cubed. That's a cubic. It looks kind of like this if you remember my interpretive dance, which of course, how could you forget? So I can go ahead and solve for the inverse of this function. So y equals x minus 2 cubed. I switch my x and y. X equals y minus 2 cubed. The first thing I need to do to undo that cube is take a cube root. So I get the cube root of x equals y plus 2. I don't know why that became a positive. That's a negative. Y minus 2. I'm going to add 2 to both sides. So I get the cube root of x plus 2 equals y. So for this function, its inverse is going to be the cube root of x plus 2. Last, I just want to say some important facts about inverses. So for every 1-to-1 function, an inverse exists, right? Every single, hi Bobby, I'm almost done. Every single 1-to-1 function has an inverse. That's good. Second, the domain of my function f is the range of its inverse, right? That makes sense, right? Because my x and y's change. The range of my function f is the domain of the inverse. If a point AB lies on my graph of my function, then of my inverse function always has the point BA. Last but not least, and this is the only one that's not really like counterintuitive, is that my graphs, what they are is they're reflections of each other across the y equals x axis, right? If I change that, then my x's become my y's and my y's become my x's. So they're a reflection across that line. So that's everything you need to know for section 6.2. We'll be talking about section 6.3 real soon.